Hi everyone, welcome back to class 2. Before we jump into today's deep learning models, let's take a few minutes to connect what we have learned so far to where we are headed. In class 1, we cover some really powerful classic machine learning models: linear regression, logistic regression, decision trees, random forests, and support vector machines. These models are great when the data is structured or the pattern are relatively simple, and very important when we already know which feature matter. But here's the challenge. What if we don't know how to extract the right features? Think of the image classification. It's really hard to tell a traditional model, hey, focus on edge or curves, unless we manually create those features. And that's where deep learning comes in. It doesn't just learn how to predict, it also learns what to look at. Why we use deep learning? Deep learning is essentially a family of models that learn hierarchical representations of data. So in traditional machine learning, we might give a model a bunch of engineered features. But in deep learning, we feed this model the raw data, like pixel values or word sequences, and the model figure out the features by itself. That makes deep learning especially powerful for the images, text, speech, sequentials, and time series. And today, we are going to see some of those deep model in action. So let's start from the neural network, because neural network is at the core of deep learning. It's made up, no, it's made up of layers of neurons and or nodes. Each neurons takes input, does some math, and pass through the result to the next layer. And there are some three main types of layers. The input layer, which means where your data enters, one or more hidden layers where the learning happens. And at last, there's an output layer where the predictions come out. Each connection between neurons has a weight, which determines how strongly a signal is passed, and each neuron applied something called active function, which decides how much the signal goes through. And we will want to know something about the activation function. Let's quickly look at two important activation functions, sigmoid and ReLU. So first one is the sigmoid function. We can see here it squashes the value into a range between 0 and 1. And it's great when we want to interpret the output as a probability. But it also has a drawback. The gradients get really small for big input, which makes the learning slow in deep networks. And another activation function is ReLU, or we can call it the full name, the rectified linear unit. It's now the most commonly used for the activation function in deep models, and it simply outputs the input if it's positive and zero if it's negative. So the advantage is fast, simple, and works well in most hidden layers. And then for the output, we might want to know about the MLP. We can call it, the full name of it is multi-layer perception. So before we jump into the CNN or RNN, we will briefly mention this one. So MLP is a classic fully connected network. Each neuron connects to every neuron in the next layer, so it's a great place to start conceptually, and it works well for structured data like Titanic dataset we used last time in our last class. But there's also some limitations we might want to mention later. So it doesn't scale well to images because there are too many connections. It connects every neuron. We will have a lot of pixels in one image. And another one is it doesn't handle sequential data set like text or time series data. So that's why we need specialized architecture like CNNs or RNNs. They are still neural networks, but with smart structures built for the special type of data. So to sum up, I want to mention 0 points here. So first one, traditional machine learning models require manual feature extraction. Second one, deep learning automates these by learning features from raw data. Three, neural networks are built from layers of neurons with weight and activation functions. Last one, MLPs are starting points, but CNN, RNNs, and transformers are built on top of these same foundations. So now um, that we have covered the core ideas, and let's look at how neural networks see and interpret images using our first deep model, the convolutional neural network. So, all right, now we are going to explore one of the most famous and most important and successful types of neural networks, the convolutional neural networks. You might also heard that before or called it CNN directly. So CNN are the gold standard for image classification, medical imaging, object detection, and face recognition, lots of or a bunch of image tasks. But before we dive into the code, let's really understand what makes the CNN special. So why now we just use the fully connected networks? Let's say we are building a model to recognize images, maybe digits, cats, or traffic signs. If we try to feed all the pixel values into a fully connected layer or MLP, we will run into two big problems. First one is too many parameters. Even a small 100 by 100 color image has around 30,000 values. Connecting all of those to just one hidden layer will require millions of weight. And the second one is no sense of spatial structure. An MLP sees the pixel values as just a list of numbers. It has no idea that nearby the pixels form edges or the textures. You might also learn that from the image processing. It doesn't understand that a circle in the top left and a circle in the bottom right are still the same shape. So we need a model that's smarter about visual data. That's where the CNN comes from. And what makes the CNN special? CNN are built to work specifically with images, and they are inspired by how our visual cortex work. Neurons that detect patterns in small regions and gradually combine them to understand complex shapes. There are three key ideas behind CNNs. First one is to use local connections. Um, And instead of the connecting every input pixel to every neuron, so the CNN will use filters, or we call it kernels. A filter is a small matrix like 3 by 3 or 5 by 5 that slides across the image. At each step, it does a dot plot between the filter and a small region of the image it's covering. So this operation is called convolution. The idea is the same filter is used across the whole image, and that's weight sharing, and it reduces the number of parameters. And different filters learn to detect different features. One might detect the vertical edges, another might detect curve, and later future filters might detect eyes, face, and textures. And second one is the straight and padding. And so we have the straight and padding. Straight is how far the filter moves each time. If straight is 1, it checks every pixel. If it's 2, it skipped every other one. And for padding, padding adds extra pixels around the border so the output doesn't shrink too much. Without padding, we lose edge information. So padding helps us to preserve the special size of image for the deep layers. And last one is pooling. After a convolutional layer, we often use a pooling layer, usually max pooling. What's the max pooling? It looks like at a small region like 2 times 2 or 2 by 2, and outputs the maximum value. And at the same time, it shrinks the size of data while keeping the most important information. The pooling gives us the translation invariance. Our model still recognize patterns even if they move slightly in the image. So, how do we build a CNN? It typically looks like this. We can see here the convolutional layers extract patterns, and ReLU will add non-linear linearity, like just like in MLPs, and pooling will reduce the dimensions and highlights the strong features. And also we have flatten. It turns the 2D feature maps into a 1D vector. And last, the dense layer, it make the final decision. And why the CNN works so well on images? There are three main reasons CNNs are such a good fit for images. First, they detect pattern locally, so they are sensitive to edges, corners, and shapes. Second one, they reuse the weight across the space, so they can detect patterns wherever they appear, not just in one fixed spot. And the last one is they are efficient. A CNN might only use a few thousand parameters for what would require millions in a fully connected network. What does it actually learn? So one of the most fancy part is we can actually visualize what each filter is learning. So the early layers might learn to detect simple edges or textures. And middle layers starting combine features into parts like circles or corners. And deep layers combine those parts into objects like faces and digits. So CNN build a uh, hierarchy of concepts like our own vision system. And what we will do in code demo in next part, we will build a simple CNN for image classification. So let's go to the code demonstration part. In this part, we will use the dataset of MNIST digit classification. This MNIST dataset contains 70,000 images of handwritten digits from 0 to 9. Each image is 28 times 28 pixels in grayscale. And it's small, clean, and perfect for beginners. So let's get started. The first step is for loading and preparing the dataset. So this line, X train and Y train, download and load the MNIST dataset into training and testing set. And here the X train and X test are image data, and Y train and Y test are the corresponding labels, which means the digits 0 to 9. And the following lines, X train and X test, here we normalize the data in the image data. So because the MNIST images originally have pixel values from 0 to 255, dividing by 255 scales down to 0 to 1 range, which helps the model converge faster during the training. And let's go to the next few lines. Here, we reshape the data into format that TensorFlow expect. That's the TensorFlow is a package we usually use in deep learning. So we have samples, height, weight, and channels. And these images are grayscale, so the number of channels is 1, and for RGB, it will be 3. And we reshape the data into the format. And then let's go to the next few lines. The labels are just numbers like 3, 7, or 9, so we convert them to one hot encoded vectors so that the model can predict the probability distribution across all 10-digit classes. And we also print the shape of training set and testing set. We have several samples here, the number of samples. And then we go to next step, build a simple customized CNN. Let's look at the model architecture here. So we can firstly break down the line. This line, the conv2d, this function, and this layer means this layer use 32 filters. Each of the size is 3 by 3, and it slides over the image and learn features like edges or curves. And we define the activation function is ReLU. So after the convolution, we apply ReLU function to introduce nonlinear linearity. And we can see the max pooling to D function. So these reduce the spatial dimensions, or we call it downsampling, and keeps the strongest features. We repeat this several times. In that case, other convolution layer with some filters and following by the pooling. And then we flatten the 2D feature map into 1D vector using this function flatten. And then we have dense layer dense 64, a fully connected layer with 64 neurons. And then this 10, and which means our output layer with 10 unit for digit 0 to 9 and use the softmax function to give us the probabilities. And we can print using this function to print the structure of the model itself. You can look at here. Okay, so let's go to the step 3, the summary for the model structure. So let's look at it. So this shows the output of shape, and convolution layers, each layers. And step 4, compile and training the model. So we can look at the function here to compile or to run the model. So we have the several lines here. For this line, we use the Adam optimizer. Adam is an adaptive optimizer that works great for deep learning. And here, the loss function, the categorical cross entropy loss function, is the function for multi-class classification you will usually use in the similar task. And in this line, we also track accuracy as our performance matrix during the training. And for the few line here, we can see we train the model for 5 epochs, meaning the model see the entire training set 5 times. And we have batch size 64. That means we process the 64 images at a time because that's very large data. So we have the batch size. And then we reserve 10 percentages of the training data for validation to the monitor the performance. So we can see the print of the training process below. So you can see the accuracy increasing and the loss decreasing over time. By the end of training, we reach the accuracy of 99 percentages, and we can see the loss function and nearly 99 percentages validation accuracy, which show the effectiveness of our model. And then we go to next step, the evaluate on test data. So this gives us the final performance on the unseen data set. So we can see the test accuracy is 99 percentages. So that means our CNN is doing a good job to recognize the handwriting digits. And we can also to see the plots and to visualize the accuracy. So the training and validation accuracy we see here both rise quickly and stay high, and there's almost no overfitting thanks to the simple MNIST dataset. And then we will go to next step, the make and visualize the prediction. So this gives us the predicted digit class for each test image. So we visualize them, and here you can see the result. The model correctly predict the digits like 7 to 1, 0, and 4, and so on. So it's confident and accurate on these simple samples. Here, the CNN has only 2 convolution layers and trains in a few minutes and hits 99 percentage accuracy. So we have also seen how to pre-process image data, how to design and stack layers in Keras, and how to monitoring the training and interpret the result, how to make prediction virally. So now we have built a customized CNN from scratch, and I will show you some real-world CNN that are often designed for the template. So these are tried and tested building blocks that inspired on deep learning model we use today, and you can build your own networks by following these patterns. So there are LetNet 5, which is an original CNN architecture from 1990s, developed to recognize handwriting zip codes. Even though it's old, but it's inspired everything that followed. And another one is VGG. So that's also a typical neuro CNN, a deeper CNN model from 2014, and it's famous for using only 3 by 3 convolutional filters, but studying them deeply. And so the key idea here, we can use multiple. Oh, sorry. So after this class, you can try to use the build up your own customized CNN or use some famous CNN architecture to apply it on different type of data. There are a lot of public data sets you can use to test this idea. And next one, we will go to the RNN and LSTM. So let's go to the RNN first. We have seen how CNNs are great for spatial or image data. And let's move to a new kind of problem, the sequences like text, speech, or time series data. These are temporally ordered, and the position and history matter. So let's look at how we model that using the recurrent neural networks. We usually call it RNNs. So why do we need a new kind of neural network? Why we use RNN? So far we have looked at models that works on the fixed size data, like images or structured features. These models assume that the input has no meaningful order. But what about data where order matters? Think of a sentence where word order determines meaning, and the time series where yesterday's value affect the today's, and a spoken phrase where the beginning determines the text context of the end. So in all these cases, the past matters. And traditional models like CNN or MLPs doesn't have memory. They don't have memory, so that's where RNN comes from. So what's a real RNN? An RNN or recurrent neural network is a neural network designed to process sequential data by maintaining a form of memory across time steps. At each point in the sequence, the RNN will take in the current input and combine it with the memory from the previous step, and it will output a new hidden state and possibly a prediction. You can think of a hidden state as a running summary of everything models have seen so far. And you may want to know how does the RN cell work. So imagine that imagine the RNN as a little neural network that loops over time. At each step, it takes the current input and takes the previous hidden state, and it adds them together, multiplies by learning weight, and applies a nonlinear function like tangent function, and the result in the new hidden state. So that hidden state is then passed to the next time step to continue the sequence, and optionally to an output layer to make a prediction. So each hidden state is influenced by both current input and the history of everything seen before. So let's visualize the RNN through time. So we often unroll RNNs to see how they behave step by step, like a chain of cells. So each RNN cell receives an input xt from the sequence and passed hidden state ht to next cell and produce an output like a prediction or intermediate representation. So the hidden state carries memory forward. So the model can learn how previous events influence the current one. And I will show you some, I will show you a very little example here. So predicting the next word. Let's say you are processing the sentence, I'm going to the. When the model reads the word the, it uses the current input the and the hidden state, which summarize I'm going to. So from these, it might predict store or movies. So that's how RN use the context to make better predictions. And what can RN do? RN are powerful tools. So for all kinds of sequential tasks, so it can do the text prediction, like the complete new word generation and speech processing, like converting audio to text, music generation, predicting the next note in a melody, or sensor analysis to predict the future values in time series. So if the data comes in temporal order, RNN can help you to learn from that. But there are some few limitations of RNN. They are not perfect. So one of their biggest challenge is the vanishing gradient problem. Here's what it means. So when the network learns, it uses the back propagation to adjust its weight. But for an RNN, this gradient have to pass through many times step. So with each step, it shrink. So sometimes so much that earlier steps cannot learn anything at all. So that's why the RNN often forget the long-term dependencies and tend to focus only recent input, and they can be slow to train because each step depends on one before. So what's the inside of the hidden state? The hidden state is just a vector of numbers. It doesn't look like anything meaningful to us, but to the model, it stores all the features and it has learned to track. So if you are processing the sentence, the stock price dropped after the news. When the hidden state might remember the word dropped when predicting the tone or the next phrase. These learned representation are the key to how our understand sequences. So we will introduce LSTM structure and to see how it solves the vanishing gradient problem in our next section. So for this section, we just focus on RNNs. So now we know the RNNs are built to model the sequences by passing memory, or we call it hidden state, from one step to the next step. And at the same time, they learn temporal relationships between data points. They are useful for text, time series, speech, and more. But they struggle with long-term memory and can be slow to train. So LSTM is the improved version that handles the longer dependencies. Let's now walk through a working example of recurrent neural network in action, and we are going to build a model that learns how a short character sequence and predicts the next character letter by letter. So let's go. To read the code, the first step, we will generate the sample data. We are using a tiny and custom string hello world. Let's see here. This sentence gives us that as an example. It gives us a repeating pattern that our RNN can learn from. So first, we convert the characters into a vocabulary. We can see the following lines. Especially for I will introduce the first two lines. So it creates a lookup table to map each character to an index or to number. So we also print the vocabulary here. We can see in the result part, the space 0, D equals to 1, A equals to 2. We have the vocabulary. There are 8 Unicode characters in string, so our vocabulary size is 8. Next, we encode the text as numbers and prepare the training samples. And we can see the preparing, we use the array function to create that. So we will go to the next step to prepare the input-output pairs. So we have the sequence length equals to 5. This means we are teaching the model given 5 characters, predict the 6th. So from the input hello, HELLO, the model should learn to predict a space and so on. So we can see the input shape, X shape is 18.5, means 18 sequences of length 5, and the labels Y shape is 18.8, so that means one hot encoded for 8 possible characters. And then we will build up our own RNN network. Let's see the model using the function sequential to build our own network. So we can see here this line, the embedding function, it's an embedding layer. It turns each character index into an 8-dimensional vector. Think of these as a learnable way to represent the characters more richly than just their index. And we go to the next function, the simple RNN. So there's our RNN layer with 32 hidden units. It processes the 5 characters input one step at a time and maintaining a hidden state throughout. And then we go to the last sentence or last line, the dense layer. So that the output layer gives us a probability distribution over 8 possible characters. And here, here the model is trained to see, say, giving these 5 letters. Here's the most lead, like the next one. So we can also see the summary of the model. Here's the summary, and it just 1,640 parameters total. That's very lightweight. And then we will go to the next step, the step 3, compile and train the model. So we compile with use the compile function, and we have the loss function here, and still use the Adam as our optimizer. So the categorical cross entropy function is standard for multi-class classification, and adapt, as I said, is a fast and adaptive optimizer. Then we train for 100 epochs. We can see the epochs, and we can see use the feed function. So the output shows here. So the final training accuracy is 100%. This means the model perfectly memorized the training patterns, which makes sense because it's a short and repetitive data set. And we plot the training accuracy. So you can see it start low and it gradually improves and hits 100% accuracy after around 80 epochs. So this confirms that the model is learning the temporal structure in the character sequence. So let's go to next step, the predict next character. We test the model used the seed HELLO. The model sees the sequence hello and predicts the next character. Its output. The output is space. So, which is exactly right because the next part of string is HELLO and space. So you can try the other input too, like space WORL should predict a D, or ELLO space should predict a W. So you can test that after this class. I really encourage that to make you understand better to the RN network. So what did we just see? We created a tiny sequence dataset from scratch, and we encoded the characters as numbers, then embedded them into dense vectors. And we trained a simple RNN to remember the patterns, and we got a model that can predict the next character with perfect accuracy. This is a great proof of concept of what RNNs can do with sequential data. And in real world, you will scale this up to predict the next word in a sentence, forecast the next hour of stock price, detect patterns in heart rate signals. But for now, we have seen the core mechanics of how hidden state memory and temporal processing work inside an RNN. So you might want to go to LSTM now. As I said, RNN also have some limitations. So we have seen how RNNs work and even build one in code. So it's time to talk about one of the most important upgrades in deep learning for sequential data, the LSTM, or long short-term memory network. So why do we need LSTM? Remember how a basic RNN works. At each time step, it takes in the current input and combines it with its memory from previous step called the hidden state, and it produces an output and a new hidden state. It's great, but it gives us a short-term memory. When the sequence get long, what will happen? The basic RNNs start to forget why, as I discussed in last section, because of something called vanishing gradient problem. When we train the model, using back propagation through time. The gradient, which tells the model how to update its weights, shrinks more and more as we go further back in time. So the earlier time step get almost no learning signal. So this means the model cannot remember information from far in the past. Think about a sentence like I went to the restaurant and the food was absolutely delicious. A basic RNN might remember the food was, but will forget the restaurant because it happened too many steps ago. That's why our LSTM comes here. So, what's the LSTM? Let me introduce that to you. So, LSTM stands for long short-term memory. It's an advanced version of an RNN that was specifically designed to remember things for longer. So an LSTM cell doesn't just pass one hidden state from one step to next. It passes two status. One is a hidden state, so just like a normal RNN, and second one is a cell state, which acts like a long-term memory. So the key idea is that this cell state can carry information across many time steps without being overwritten. And the network learns how to control what gets stored, removed, or passed along. This is done using the gate. And how does the gate, the LSTM gate work? There are three types of gate inside RN or sorry, the LSTM cell. We can look at this table. So the first one is forget gate. This gate looks at the current input and previous hidden state and decides what part of the previous cell state to forget. And next one is input gate. So this gate determines what new information should be added to the cell state. And it's like deciding what's important enough to save. And the last one is output gate. This gate decides what to output. That is what part of the cell state should influence the current hidden state and the final prediction. So the full LSTM cell is like a smart memory manager. It knows what to remember, what to forget, and what to focus on. And it learns to do this from data. And go to next part. What does the architecture looks like? If you unroll an LSTM through time, just like an RNN, so each time step still passes information to the next. But inside each step, there's now much more control over memory. You can think of like these from input, we go to LSTM cell and LSTM cell, several cells, and we go to the output. And in each LSTM cell, we can look at the current input. We have the memory. It's carrying from past. We make a series of decisions using a gate, and we update its internal memory and pass everything forward. This is internal memory or cell state is the key to make or to what makes LSTM powerful. And where are these LSTM used for? So they are everywhere in sequential modeling. So, for example, in language models, they help remember the topic of a sentence or paragraph. In time series forecasting, they can remember long-term trends and patterns. And in speech recognition, they can help understand the full context of spoken phrase. In medical data like ECG and EEG signals, they can help track long-term trends in patient data. So they are a core building blocks of many state-of-art of in NLP systems and are still widely used today, even alongside more modern architectures like transformers. So if we compare the RNN and LSTM from this table, shortly, it's smarter and more stable and more powerful when dealing with complex sequence. So for a key takeaway, it lets us learn from the past and remember what matters and forget what doesn't. So in the next section, we will build an LSTM model in code and train it on a sequence prediction task, similar to what we did with RNN, but more powerful. Now let's go to build it. All right. Now, that you have seen the concept of LSTM, how it works, why it's better than a regular CNN, let's walk through actual code demo. We will use a really small data set, just the phrase hello world, to keep things simple and visual. And our goal is to train a model to predict the next character in the sequence. That means if I give it, it hello as input, I want to tell it to tell me that the next character like a space, because that's how the original phrase continues. We still define the text, hello world, hello world. This is our training data, and it's short and contains repeat patterns, perfect for seeing how memory helps learning. And now we want the computer to understand letters and numbers. So we still build up vocabulary that's a mapping from each character to a number. And we still have the output here. Space is 0, D is 1, and so on. And then we convert the text into a list of numbers using the dictionary. We can call it dictionary with the array function. And this gives us the numerical version of the sentence, which we can feed into the neural network. Then we will build the training samples. We have sequential length is 5. This means we are telling the model, I will give you 5 characters and you need to predict what comes next. So one training sample would be input HELLO and target is 0, a space. And we use a loop to extract many such samples from the sentence. And then we have X, Y, and the for loop. We now have X as a list of 5 character sequence as input, Y as the next character after each input. There we call it labels. And we convert the labels using this line. Convert the labels into one hot encoding for classification using this function. And now look at the shape of our data. After pre-processing, we print the shape of the data set and we get the for the input 18 examples, each 5 characters long, and for the Y shape, 8 possible characters means each is one hot encoded. This means we will train our model using 18 examples, where each example is a 5-letter input with one output. And let's go to the next step, building the LSTM model. So, build our LSTM now. Still the function sequential. And it's pretty similar to the how can I say, to the RN model. So embedding function, that this embedding layer converts numbers into vector representations. It learns an 8-dimensional meaning for each character. For example, the h might become 0.3, negative 0.1, and guess the h is 3, so it can be different values. So then comes to LSTM, not RNN in this time. So it's a heart of our model, and it processed the 5 characters one at a time, maintaining the internal memory as it goes. And it has 64 units, like 64 little memory cells inside that it uses to remember uh, important features of the sequence. And finally, we have the output layer. The layer output a probability of each of 8 characters, and the model will guess which character is most likely to come next. And we go to the model summary. We can always use this function to get our shape of model. So we can see the total parameter get increase to a very large number, 19,272. Most of those are in LSTM layer. This is where the learning happens. So compared with the basic RNN we used in the last section, LSTM will have more internal complexity, but that will allow it to remember longer patterns. Then let's go to the step 3, compile and training the model. We compile it, use the compile function. This means we are using a loss function designed for multi-class classification. And the DAM optimizer is a great for training deep models quickly. And then we train the model use feed function as we always did. We train for 100 epochs, and on each round, the model see all 18 samples and updates its weight. And go to next step, visualize the training accuracy. We visualize how accuracy changes over time. So here we can see the accuracy starts low still, then the model is just guessing. And then it slowly improves, and especially after 50 to 60 epochs. By the end, the accuracy hits around 83 percentages. It shows that the model is learning the sequence pattern. It remembers what character usually comes next. And then we will do a prediction. And you can also do similar after this class. And this is just a starting point. Seed hello, and it's pretty similar to last step. And output is also space, which is correct. And so now we have learned, we trained a real LSTM model to understand sequence, and it learned how characters in Hello World related to each other, and it can now predict the next character. based on the given sequence. Even though the dataset is very small, the demo shows the power of LSTM memory. It can learn when and what to remember, just like we talked about earlier. So you can do the experiment after this class and to see what happened by yourself. Then you will understand deeper about this part. Now, all right. Now we are going to explore one of the most fascinating rules in the deep learning, generative adversarial network, or we call it GANs. So you recently the generative AI is pretty popular. So GAN is one of the generative model. So what makes it special or what's it? So far, we have seen models that recognize things, classify digits, predict labels, understand sequences. But GANs are different. GANs don't just understand data, they create it. They can generate realistic images from scratch. For example, it can create new human face that don't exist. And it can turn a sketch into a photo. It can fill in the missing part of an image, create new artwork or anime characters. They are the model behind deepfakes, AI art, and even synthetic data in scientific research. And we can see the structure of GAN here. The GAN is made up of two neural networks working in opposition. There's one generator, like Fogger or artist. It starts with random noise, just meaningless numbers, and it learns to turn that noise into something that looks real, like an image of number or a face or a shoe. And there's also a discriminator, like a detective. It sees both real images from dataset and fake images from the generator and learns to classify. Is it real or is it fake? The key idea here is the generator tries to fool the discriminator, while the discriminator tries to catch the generator. It's a game, and each network pushes to the other to get better. And I can introduce the training loop of the game to help you understand that concept. We can go through what happens during training. So we will start with random noise, like 100-dimensional vector of random numbers. And then the generator turns that noise into a fake image. The next step is the discriminator sees two images. One is the real image from training data, and the other one is the fake image from generator. And then the discriminator tries to predict correctly. One is real, zero is fake. Then the generator updates its weight to make the fake image look more realistic, to fool or to cheat the discriminator. And this loop continues for thousands of iterations to generate the real images. Over time, the generator gets better at generating, and the discriminator will get better at detecting until ideally the fake image are indistinguishable from the real ones. So what's the goal of the the GAN. So the goal is for the generator to learn underlying distribution of real data. And in simple terms, the generator should learn how to make new images that look like they come from the the dataset, even though it's never seen them before. That's what makes GANs generative. They can imagine new samples that were not in the training set. And let's see what can the GANs actually do. I can give you an example uh, of the task. There's several tasks: image generation, data augmentation, um, uh, the style transfer in painting, and domain transfer. So we can regarding those things, and we can know how it can do. And I will just introduce the basic again in this class for code demonstration. And you can also search on internet after the class and to see how the bunch of type tasks, how they work with the GANs. And we will maybe I can just give you a few exciting examples. Like there are several GAN, like the style GAN, can generate high resolution of people who do not exist. And pixel to pixel and cycle GAN can turn line drawing into photos or convert summer landscape to winter. And there's also GAN in medicine to help generate synthetic MRIs, CT scans, or the skin images. Extremely useful when the real patient data is scarce. So GANs can even denoise blurry images, create the super resolution versions, or perform image to image translation. And behind that, let's talk just a bit about what's happening internally. So the generator is usually a deep neural network that upsamples noise into a full-size image, kind of like a stretching. They are stretching and shaping static into structure. And the discriminator is often seen a classifier trained to say real or fake. During the training, the generator is trained with gradients from the discriminator's judgment, so it slowly improves based on how badly it got caught. And the whole model trains using the two computation loss function, one for discriminator, can I spot fakes, and one for generator, can I make fake that pass. So it's powerful, but not easy to train. There's some challenges. So the model copies the generator produce the same image over and over, and the losses swing back and forth. Also, the game never ends properly, and it will never converge. But over the years, technicals like the label smoothing or progressive growing that helps stabilize the gains. So we have learned some knowledge about GANs. They are made of two networks, generator and discriminator, and the generator learns to create realistic images. The discriminator learns to detect fakes. Together, they improve each other, and they are used in the AI art, medicine, fashion, and entertainment. And they are hard to train, but can generate the realistic content. And now we are going to build one. We will write a simple GAN to encode and learns to generate the fake handwritten digit, like the MNIST numbers you have seen before. Let's go to create something from scratch. All right. We will do this with a simple GAN. We will hit all key ideas, generator, discriminator, and everything. So for the first, we will load and prepare the MNIST data. So xtrain loads the MNIST dataset, 60,000 images of digit. And we only use images, not labels, because the GANs are unsupervised. It just generates but not classify. So for these two lines, we normalize the pixel values to between 0 and 1. That's important for the stable training and simple training. And then we flatten each 28 by 28 image to 784 element vector. The final shape becomes here. We print it out 60,000 and 784. This is now ready to be passed into our discriminator as real data. And then we will build up the GAN together. We will use the build generator to build the generator and build the discriminator. So we will start from the generator. We define a function. Here, use def, define the function to build our generator, which is a neural network. And we are using Kara's sequential model, which stacks layer one by one. And then we have the dense. The dense is the first dense layer of our generator. It takes an input vector of 100 random numbers, or we can call it pure noise. And then it output 128 neurons, which serve as intermediate features. And this layer learns how to expand noise into something useful. And the leaky value, we use leaky value activation function instead of value to avoid dead neurons, which means if a neuron gets stuck at 0, it still gets a small gradient to recover. Let's go to next one, the dense. This layer output 784 values, one for each pixel in a 28 by 28 image. And we use a sigmoid function to squash all output between 0 and 1. And the matches that matches the scale of real MNIST images. And the reshape function, we reshape the flat vector into a 2D image to 28 by 28 pixels. So we can visualize it and pass it into discriminator. And finally, we will use return to return the generated model. And for the discriminator, we can see we define the function which tries to detect real and fake images. So that's not same to the generator. We have the flatten function. The input is a 28 by 28 image, so we flatten it to 784 dimensional vector, and it's allow us to fit it into dense layers. And then we have dense 128. We use a hidden layer of 128 neurons to process the image. And then still we use the leaky value to help avoid dead activations. And for the last dance, the final neuron output a single value between 0 and 1. So if it's close to 1, the discriminator believes it's a real image. And if it's close to 0, it will think it's fake. Return the discriminator. So I have a pretty similar here. So to build and train again. So we have discriminator compile to compile the discriminator. Let's start from the initialize the build the models. So we use the generator and discriminator build this function to initial or instantiate both models. And for the next one, the next line, the discriminator is a small trick. So we call the discriminator once with dummy data. And this helps TensorFlow to initialize all the internal variables before compiling. And then we go to next step on the compile discriminator. So we define the loss binary cross entropy used for binary classification, real or fake. And the optimizer is DAM, a good default for most deep learning task. And the metric accuracy to track how well it distinguishes images. And for next line, we freeze the discriminator weight for GAN training, so only the generator learns during the phase. And here for several line, we define the GAN model. It takes a random noise vector Z and pass it through the generator to create a fake image, then send the fake image into discriminator. And then the final output is the realness score. So to the last step, we compiled again. And during the GAN training, the discriminator is frozen. So we only update the generator so it can fool the discriminator. And for the training, we can see here. So we define the train GAN. We have to define a function, or we already define function for the deep learning model training. So for number of epochs, 1,000 epochs, batch size, and we will train discriminator on half of the batch with real and fake images. Loop over the, and it will loop, continue loop from the ranges or each epoch. And we will train the discriminator here and here and train the generator with those lines. So for the discriminator, we randomly select the half batch real images from the training data, and we generate the half batch fake images from random noise using generator, and we train the discriminator on real images labels as 1 and fake images labels as 0. It learns to separate them. And for the generator training, we will generate a batch of noise. And this time we label the discriminator output as 1. And this means we are asking the generator to create images that discriminator thinks are real. In this step, update only the generator. And we can we have the loss function here. We can observe. So every 200 epochs, we print the discriminator and generator loss and realize the generated digit. And then we will go to the show generated image function. So because we want to visualize the result of again, so we create n fake images from the generator, and then for the following lines for the plot group of plot, we use the matplotlib library to plot the generated digit in a single row. And then we will go to the final step to call this function. So normalize the pixel values to 0 to 1 and reshape to 28 by 28, and we run the training for 1,000 epochs. And we can see the result here because I have very limited time now, so I cannot show you the whole result. So early in training, the generator is still confused from the noise. So images are noisy and it kind of goes more clearly after several epochs, but we have to set up the number, and you can try that after this class to see if it can generate clear images or real images. And the discriminator loss is slightly lower than the generator. It's so slightly higher than the generator loss. That's expected. And if you trained longer, maybe 10,000 epochs, you can start to see the digital shapes. So for the rest of time, I will briefly, okay, here's the two typical again, and you can know and learn after this class. And for the rest of time, we will go to the transformers. Okay, so in the rest of time, it's short, so I will briefly talk about transformers. They are one of the most important breakthroughs in modern deep learning, especially for languages and sequentials. Before transformers, most NLP neural language processing models were based on recurrent neural networks, or RNNs. This model process one word at a time in order, just like we read a sentence. But that also means they're pretty slow and they struggle to remember long-term dependencies. If the important word was 20 steps earlier, the RNN may have already forgotten it. Transformers changed everything by removing recurrence. Instead of processing tokens one by one, transformers read the entire sentence at once, allow them to find relationships between words, even if they are far apart in the sequence. This is made possible by something called self-attention, which is the core idea of transformer. So let me explain what self-attention means. Imagine that there's a sentence like the animal didn't cross the road because it was too tired. To understand what the it here stand for, um, so a model need to look back at the animal. That's what self-attention does. It allows every word to attend to or pay attention to every other word in the sentence. So instead of the reading left or to right blindly. The model is learning where to look for context. Now inside a transformer block, our word turn to um, our word turned into a vector, and each of those vector is projected into three rows: a query, a key, and a value. The query from one word is compared with the keys of all the other words to decide which are most relevant. Those scores are then used to weight the value vectors, and the result is a new contextual representation of each word. This is self-attention, and it allows words to gather useful information from the rest of the sentence. But the transformer doesn't just compute attention once. It uses what's called multi-head attention. So it means the model computes self-attention in parallel using different sets of weight. Each head may focus on something different. One may look at grammatical structure, while another may find subject-verb agreement or some thematic connections. The result from all head, they are then combined and passed through a feed-forward network, just like a traditional deep learning layer. So now you might wonder, if there's no recurrence or time steps, how does a transformer know which word comes first? So here that's handled by something called positional encoding. These are special patterns added to the input and embedding to help the model distinguish the order of words. So you can think of them as unique and repeating wave signal that encode the position without adding recurrence. Each transformer layer consists of a few key parts: a multi-head self-attention mechanism, a small feed-forward neural network, and feed-forward layers, and two very important tools: the residential connections and the layer normalization, as I put here. So residual connections help the model keep useful information flowing from early layers, and the layer normalization helps stabilize training and prevent vanishing gradient. All of these combine into what's called transformer block. So when we stack several of these blocks together, we get a transformer encoder, which is great for tasks like classification or sentence embedding. If we add a decoder, we can do tasks like machine translation or text generation, where the output is also a sequence. This full encoder and decoder structure is what originally proposed in the paper "Attention is All You Need." That's the first paper that come up with the idea of the transformers. Now, why does it matter? So because the transformers are the heart of almost every major language model today. We have some examples like BERT, GPT, Vision Transformer, and ChatGPT. So some of them are really famous and you must heard of them. And of course, ChatGPT. It's a transformer at scale and trained on a massive corpus to understand and generate human-like responses. So how do you use one? So the amazing thing is you don't have to build the transformers from scratch. So there's a Hugging Face Transformers library. You can load a powerful model in just a few lines of code. So for example, here, I will give a very mini examples here. So before do that, you have to use the pip install to install the library. And then there are two mini demos I want to show you. So for example, for first one, if you want to sentiment analysis, you can write as here. So it will return a sentiment prediction like positive with a confidence score. And it use a pre-trained model like these two birds under the hood. And just like here, the positive and 99, even 100, almost 100 positive give you the altitude of this workshop is really fun and informative and it's positive. So that means the sentiment. And if you want to summarize a long text, you can see here the text transformers have revolutionized NLP by replacing something. So if you want to summarize, you can use this function and in both, and you will get result here. So in both examples, you didn't have to define attention, train a model, or tune anything. The magic is already built in, and that's the power of using the pre-trained transformers. So I highly encourage you. So after class, you can look into this library in details and try by yourself to try different functions, different model to see what will happen after you did that. So, all right, that brings us to the end of our deep dive into the modern machine learning and deep learning models. Over the past two class or sessions, we have gone from the fundamentals like linear regression all the way to some of the most powerful tool in AI today, CNN to image recognition, LSTM, GANs, and transformers. And what I hope you to take away from this class is not just how to use these models in Python, but why they are so important. So we saw how just a few lines of code can unlock uh, incredibly. So whether it's summarizing an article or detect something, and more importantly, we explored what's happening under the hood. So I want to encourage you to keep experiment, try to load in for a different dataset, changing hyperparameters, or even explore new models like diffusion model or vision transformers. Everything we did today is just beginning. So finally, remember to the best way to learn machine learning is by building by yourself. Thank you all for so much for your attention and see, and I'm really proud of we have covered together. So I hope you leave today not just with knowledge but with confidence. Thank you.